Good morning, good afternoon, or good evening, wherever you are located. Thank you for joining us for this AMETEK Solid-State Controls webinar on why we need UPS systems. As usual, we're going to wait for everybody to join as I see the numbers go up. And while I'm doing that, I can do a few introductions. But first of all, as I always like to do, ask if everybody can hear me. So you have your chat bar on the right hand side of your screen. If you click on the chat icon and then type in there if you can hear me, it would be appreciated. As always, I don't want to be speaking to nobody. I don't mind speaking to people and I'm not listening, but speaking to nobody doesn't sound like fun. So I'll just wait to make sure that people can hear me. Thank you very much, Tony. You can hear me loud and clear. And Javier, very good. Thank you. So my name is Craig Williams. I am the Senior Technical Manager for AMETEK Solid-State Controls, and I am located in the Stafford office, which is southwest of Houston in Texas. I've got 22 years in the industrial UPS industry. I've worked with all of the major UPS charger manufacturers from all over the world, and for the last 8 years I've been with AMETEK Solid-State Controls. So some would say that I am a subject matter expert. I do know my UPSs. There will be a lag of around 30 seconds between you hearing my voice and me seeing a question, and that's basically, we use a platform called Webinar Jam, and when I do this webinar, it's got to take the data, process it, send it out on iOS, on Android, and on Windows-based systems. So there is some processing time that's required to do that. So when I say something, you won't hear it until about 15 to 30 seconds from after it being said. So therefore, if I'm saying something and you have a question, then I'm not going to see the question until 15 to 30 seconds after I've said what I've said. Hopefully that makes sense. So what I ask that you do is, if you do have any questions, please, if you look in the chat bar, there's at the top of the chat bar, it says chat, and then there's a question mark and it says Q&A. If you have a question, please put it in the Q&A section. And at the very end of the webinar, I will go through all the questions that have been asked, and hopefully I'll be able to answer most of them. The platform that we use, once again, is called Webinar Jam, and they have a panic button. So if I see that people type in the chat bar, oh, I can't hear you, or I can't see the presentation or something, I can do a few things. And if it looks like the room that we are in has frozen or has broken for some reason, I can just press one button and it will take us all to a new room, and we will carry on from where we left off. A very popular question is, will the webinar be recorded? And yes, Webinar Jam does record the webinar, but the format that it records in it's just like another webinar. So if you want to go and watch this on the Webinar Jam platform after this webinar, you press play, and it's just as if you're watching the webinar from scratch again. You can't fast forward, rewind, or do any of the things that we're used to doing. So what our fantastic marketing department do, and London has put the link in the chat bar already, is they convert that Webinar Jam video into an MP4, and then they upload it to our YouTube channel, and then you can share it, you can play it, fast forward, rewind it, mute it, do whatever you want to do with that video. And if you use that link, you will see every other webinar that we have done is on our YouTube site. So you can go and have a look at maybe some other subjects that you have not seen yet, or you're interested in seeing. And the last thing is, the webinar should last around 45 minutes to an hour, and that always depends on how much I talk. So let's see how it goes. So the learning outcomes today are obviously understand why we need a UPS system, know the difference between a UPS and a generator. I know that many people out there I do understand the difference, but there's some people who don't know, well, why would we use a UPS when we can use a generator instead? And also understand the very basics of how a UPS works. So that's the objectives of today's webinar. So first of all, you've got to know a little bit about AC and DC. So AC is a sinusoidal waveform, and some people, they understand what the sine wave is doing, but they don't really think about, you know, it crossing past the zero crossing point here. So in this example, this portion, the current is flowing that way. Now, yes, the amplitude is changing on this portion of the sine wave, but the direction of current does not change. It just changes in amplitude. And only when we go past this zero crossing point here, does the current then reverse direction. It alternates, okay? And therefore, for this bottom portion of the waveform, the current is flowing that way. So it's kind of pushing and pulling all the time. And at the zero crossing points, there is no potential, so there is no voltage, so there is no current at the zero crossing point. So every time you cross the zero crossing line, there is no current being applied to the circuit that the AC waveform is feeding. So these concepts are very important to know as we move into why we use UPSs and generators and AC and DC. So, well, how do we make AC? A lot of people take it for granted that it just comes out of the wall socket, but that is obviously not correct. It gets made, and it's usually made by a turbine generator, okay? And a turbine generator in its most simplest form has a stator, which is stationary, and it has a magnet, a north pole and a south pole of the magnet, okay? And then if we look at this point here, point A, okay, this is where, so obviously you can see this direction arrow here. That is the rotation of the armature inside of this magnetic field. So when we're at point A, which is this point here on the waveform, we are as far away from the North Pole and South Pole as we can get. So at that point there, we're not inducing a magnetic field on the armature. It's too far away from either pole to be able to do that. So therefore, we have no voltage, which is the zero crossing point on the waveform, okay? Now, as the armature spins, you can see here, B is now getting closer to the North Pole here. And that's represented over here on the waveform. It's starting to get closer to the North Pole, therefore a field is being induced, and you can see the voltage is building up until we get to point C. Point C is the closest that the armature is going to get to the North Pole of this magnet. So that is the peak of the sine wave, okay? And now, as you can see, we're moving in counterclockwise direction. When we get to point D, we're moving further away from the North Pole of the magnet. So the amplitude or the field induced in the armature is starting to go down. And that goes all the way down until we get to point E, which is this point here. And that is a zero crossing point because we are far enough away from the North Pole and the South Pole that we are now no longer inducing a voltage. And then what happens to create the full circle, the 360 degrees that we're used to in electricity? We then move to point F, which is now getting close to the South Pole. And therefore, we have reversed the direction of the current, and we get to point F here, and then to point G here, and then point H here. And that is why, that is the only reason why the output that we see, if you put an oscilloscope onto your wall socket in your house, you will see a sinusoidal waveform. And that is because at the power generation plant, they have a generator that is operating basically on this exact same principle. It is an armature rotating through a magnetic field or it can be reversed. You can have the magnetic poles spinning around the armature, whichever way is deemed more efficient, but it always creates an AC waveform. So all the power in the world at the moment generated by the grid is AC. Now, we should all know that. Unfortunately, there is no device known to man that can store AC for prolonged periods of time. And if somebody put their hand up and says, oh, I know how you do that, well, keep it quiet, go to the patent office and put a patent in for that device, because you will make millions and millions of dollars if you have a way to store AC for prolonged periods of time. It's just not possible with the technology that we have. So a lot of people will say, well, why can't I use a generator? You know, a standby generator or an emergency generator. And in some situations, that is a possibility, but in other situations, it's not a possibility. And I will explain why. The first thing is, you know, grid power is very reliable in North America, especially, but things happen. And you can see this picture here. You can have a weather event, or you can even have a vehicle crash into a power pole, and it will take down the transformers or take down the distribution lines. It can cause damage that causes an interruption in that AC. And the problem with that is we have no idea when that is going to happen. Okay, so if you have a generator and you want uninterrupted power, you would have to run that temporary generator all the time, because you don't know when the grid power is going to fail. You have absolutely no idea. So that is why in some circumstances you can't use a generator, because it takes time for a generator to run up to speed, usually about 30 seconds or more for most standby generators. They need to start, they need to speed up, they need to regulate, and then they need to get to their voltage and say, okay, I'm now ready to get put onto load if necessary. That 30 seconds is extremely important. And remember, it can be a little bit longer than that because some loads are very critical and can't handle any power interruption. Now, for your house, it's absolutely fine. You know, your AC, your refrigerator, your lights, you know, 30 seconds without that is not going to cause any issues whatsoever. You know, you won't be able to see if it's dark for 30 seconds, but, you know, that's just an inconvenience. It's not critical to your house. And for the refrigerator or the freezer, losing power for 30 seconds while the generator starts is not the end of the world either, because it will still keep itself cool because of the insulation in the appliance. So 30 seconds to a minute to even 5 minutes for a house, it's not the end of the world. Your house is going to be okay with that. But for other applications, for example, like the DCS system, the distributed control system on an oil and gas platform, or at a petrochemical refinery, the UPS powers all of these screens and controls here, okay? And if all of those screens and controls lost power for 30 seconds, you know, we could be in really big trouble, because there is no longer overview of the operation of the plant. You can't see what position the valves are. You can't see what temperatures some of the critical pipes in the process are. Okay, and not just that, excuse me. Due to the DCS system not being able to control those pumps, solenoids, and other devices, those systems would go into a fail-safe mode, which usually means a controlled shutdown. And therefore, you have to shut down the plant, which is extremely expensive. Also, a lot more control rooms and plant operations rely on huge IT data centers to store all of the data for how much oil is going through the pipelines and is being stored, and is basically all the metering for those systems. And if you lose that data, you have no idea of how much money you're producing. So once again, very, very critical. On turbine control systems, a loss of power means an uncontrolled shutdown of turbines. On fire and gas detection systems, losing power means a loss of fire and gas protection, and that usually means everything shuts down because of that system not operating anymore. And there's many, many other systems in a petrochemical, oil and gas situation where constant power is required. And when I say constant power, I mean you can't have even a second worth of power loss. Okay, the power has to be continuous at all times. And the same can be said for data centers. Data centers is a huge business at this moment in time, because obviously I'm being a bit facetious here, but the cloud does not exist. And remember the A in AI, artificial? The cloud and artificial intelligence is all controlled by data centers. And there are data centers in pretty much every city in North America, and they are huge, and the power that they require is megawatts of power. They are extremely power hungry, okay? And the negative consequences of downtime can be enormous, not only in terms of the lost revenue and service level agreement payouts, because basically, for example, if there's a data center out there that has a deal with one of the major banks, then that bank says you cannot have any service disruptions. And if you do, then there will be penalties. And not only that, it negatively impacts the organization's reputation and customer trust. So any power outage in a data center can cause huge, huge issues, loss of data, loss of people's access to their banking data, or even more critical financial systems behind the scenes. So it's very, very, very critical information. UPS systems also prevent sudden power interruptions that can cause data corruption and loss, because they don't have time to save any of the data. So actual data could be just lost because things don't power down correctly. And also, clean and stable power extends the lifespan of servers, networking cables, and equipment and storage devices, because you're protecting from peaks, troughs, brownouts, surges, all that kind of stuff. Okay, generators can't do that. And the commonality between all of these systems, the distributed control system, the DCS in the control room of a petrochemical plant, or the server stations in data centers, is computer power. Okay, processors, RAM, all these kind of things that need these high-powered transistor technology to do all of the processing. That computer power cannot see any form of interruption in power whatsoever, or it will shut down and lose its data. And that's the same for distributed control system power supplies. All of the DCS systems convert the AC power that's generated from the grid into DC power using power supplies. Okay, and this is just an example of a data center power supply rack. There are just in a megawatt system, there are going to be hundreds of AC to DC power supplies that need to be maintained with high quality AC to keep everything running. So loss of power for more than a second, usually less than a second, and that depends on how big the capacitors are in the AC to DC power supply, means everything shuts down. Screens go off, processors are lost, everything shuts down, and it's a very bad situation. Okay, that is why you can't use generators. So for an oil and gas plant, typically they will have a UPS to supply roughly 30 minutes to up to 3 hours of power so that the plant can be shut down in a safe mode of operation when grid power is lost. So they can, from the control room, they can start a standard shutdown procedure that shuts down the process in a controlled way. That means equipment's not going to be damaged, people are not going to be harmed, everything is done in a very controlled way. Okay, so the UPS will last between 30 minutes to 3 hours. Hopefully the grid will come back on again before you get to that end of time. But that's usually what a UPS in the petrochemical industry lasts for. In a data center, the data centers UPSs are only used for a very, very short period of time, usually less than 5 minutes. And that time is all it's for is to allow the emergency standby generators to start and get up to speed. So pretty much every data center has a huge bank of emergency standby generators rated to power their whole plant. And if grid power goes off, the UPS's only responsibility is to keep power to those UPSs until sorry, not power to the UPSs. UPSs to power to the connected equipment until the emergency standby generators get up to speed, are safe to put onto load. So that's the two main differences between petrochemical and data centers. So what makes a UPS uninterruptible? It seems a simple question, especially if you know a little about what a UPS does. But it is the battery. It is the fact that we can store DC. Remember I said earlier, if you knew how to store AC, you would make millions of dollars. Well, because we can't store AC, we know we can store DC in batteries. So that is where the uninterruptible part of the power supply comes from. We store the energy in batteries, so if we lose AC power, we can use that stored energy to carry on creating AC power. And we'll go into that in just a moment. And the difference between AC and DC is you can see here, this is the waveform for DC. Now, a lot of people say, well, that's not a waveform, it's just a straight line. But that is what the output of a DC system is, a battery system is. It's completely flat DC. Well, that's what it should be anyway. And you can see here, the current never changes direction. It never goes below this zero volt line here down into this area here, which would make it alternating current. So DC direct current means the current is always flowing in one direction and one direction only. And because it doesn't cross a zero crossing line, therefore all of the connected equipment, processors, and all that kind of stuff that gets applied by DC will not lose their power. So the problem is solved. Let's just use DC. Let's use DC for everything. Well, unfortunately, or fortunately, whichever way you look at it, Tesla won the battle. You know, obviously, if you go back to when electricity was first invented, there was a battle between DC and AC. And AC won basically because we knew we could use transformers to step down high voltages to low voltages to high voltages. So therefore, we could generate power at extremely high voltages. And then when we distribute those voltages at low current, then there are less losses in the line. So that is why we use AC. So because of that, we have to figure out, okay, the grid uses AC, but we want to use DC. How do we figure all of that stuff out? And the way we do that is with a UPS. And the UPS has two main power boxes in it. The first one is on the input, and that is the rectifier or charger. And basically it takes the primary AC from the grid. Okay, so in truth, you could think about it just plugging it into your wall socket. Obviously, for most industrial systems, it's going to be three-phase 480, not 120 out the wall. And then that goes into this rectifier box, and it takes the AC, and then it changes it into DC, and that charges the battery. Okay? And we have to charge the battery. If we didn't charge the battery, then it would be classed as a primary battery, which is just like your AA's or your AAA's that you put in your remote controls that you constantly have to change. They're not rechargeable. We don't want to have to replace our batteries all the time when it's in an industrial situation. We want them to always be able to be kept at a certain state of charge so they are ready for action whenever they are needed. Okay, and then the second power block we have inside the UPS is an inverter. Okay, we need to invert the power from the battery, which is just DC, back into, so that's DC there, back into AC on the output here. So that is why we invented the double conversion UPS system. And this is the single line diagram for an AMETEK solid state controls double conversion UPS. We have our AC input going in here. Our battery charger rectifier converts that AC into DC and keeps the battery charged. And then that DC goes into our inverter, which then gets changed back into AC, which then goes out through a static switch, what I'm not going to explain on today's webinar, and then out to our AC output, which is all your load circuits, which it could be your DCS system, whatever it is that you've got connected that is critical equipment that can't lose power. Okay, so now we'll go into, well, actually, how does the charger do that? Okay, so here's our charger section here. Its only job is to convert the AC to DC that can be stored. Okay, every parameter of the charger is dictated by the battery. That, you know, a lot of people get confused. Oh, the charger has to do this, that, and the next thing because the inverter needs to do this, that, and the next thing. No, the only thing that the charger rectifier has to do is keep the batteries charged at a certain voltage. That's its only job. Okay, every parameter is dictated by the battery bank. So how do we do this? Well, we take the AC input and put it into what's called an SCR bridge, and we use 6 SCRs in our bridge. A lot of people get complicated whenever they see an electronic device like an SCR. So this is an SCR, okay? And some people, their brain just freezes over and says, oh, what the heck does an SCR do? In most power electronics, all you've got to look at this is a switch. It's either on or it is off. None of this fancy amplification regions or anything like that. It is either on or it is off. Okay, so let's say, for example, so we've got 3-phase going in here. We'll call this L1, L2, and L3. Okay, so we've got power going from L1 up to this point here. So if this SCR is off, nothing happens. No power can get through. But if we turn this SCR on, power does get through. Okay. Now let's say, for example, our output, let's just put a lamp on the output here. That is our load, it's just a lamp. Well, if we turn this SCR on, if you know anything about electricity, it is potential between 2 points. So we need to get back to L2. And if none of these other SCRs down here are turned on, there is no way that we can get back to this point here. So with only one SCR switched on, this lamp is not going to light. We need a path back to L2. So what we do is we switch this SCR, L1, and this SCR on, L2. And if you watch the power flow, that then goes out through our lamp down here, and we can get power back to L2 at this point here, and therefore the lamp will light. And if you forget about this inductor and the capacitor, if we actually connected the lamp right here, okay, and we put an oscilloscope on this point here and this point here, and let's say when we send the signal to turn these SCRs on, it's right at the start of the AC waveform. Because remember, going in, we have this AC waveform going in. What you're going to see across this lamp is you're going to see a bump like that. You're going to see this whole portion of the sine wave get through. Because remember, the SCRs are they're not fancy. They're not making DC. They're just allowing power to flow through like a switch. And then what we can do is for this portion here, we're going to say, well, L2 is now more positive than L1. So we need to get L2 up to this portion here. So what we can do in that, so this is L2, L1. We then switch this SCR on, which makes that side positive. Okay, and we go through our loads, and we have to get back to L1 at this point here. So we go all the way back here, and up there. And then, so instead of having this portion here on the negative side, we have now made it through this SCR, we have now made it positive. So I'd shown that L1 to L2 was that hump there. Now what we've done is we've now rectified that portion of the sine wave up to the top there as well. So now we have DC rather than AC, which goes one way that way and the other way that way. Where now the current is moving in one direction. We have now created DC, and that DC, its only job is to keep the battery charged. Okay. And the parameters for that battery can be slightly different and sometimes majorly different for different types of batteries. So you can see here we have lead acid, NiCad, NeMe, and lithium ion. Okay, so in the world that AMETEK solid state control lives in, the industrial UPS system, the majority of the systems are the inherent or the legacy design is lead acid, and we usually have 60 cells. Okay, that's a 120 volt nominal DC bus. Okay, and if you look at the data sheet for most lead acid batteries, they said they need to be charged at 2.25 volts per cell at 77 degrees Fahrenheit. So therefore, we have 60 cells times 2.25 volts. That means the float voltage out of the rectifier charger circuit needs to be 135 volts. So that is exactly what the battery charger, if we go back to this previous slide, when you measure positive to negative here for a 60 cell lead acid battery, you're going to have 135 volts DC. And that is why it's only dictated by the battery. We don't make it 135 volts because that's what the inverter needs. Absolutely not. It's because that is what the battery needs. It's the only reason we set the voltage at that level. And for NiCad cells, you're usually going to have 96 cells. Sometimes it's 92 cells. It depends on the engineer who designed the system and what the parameters are. And then that gets charged. A NiCad cell usually gets charged, if it's a single stage charge level, it's around about 1.42 volts per cell for a NiCad battery. And that makes a total output voltage, 96 cells times 1.42 volts is equal to 136.2 volts. So you can see there is a 1.2 volts difference between the float voltage for a 60 cell lead acid to a 96 cell NiCad. Okay, and that's important. 1.2 volts extra across a battery string can cause problems. It can cause the electrolyte to dry out, especially in valve regulated batteries. And then you can see when we go to lithium ion batteries, in most systems it can be 35, can be 38 volts. It depends on the manufacturer and design of these new lithium ion batteries, but they get charged at roughly 3.6 volts per cell. So if you times 35 by 3.6 volts, that means a lithium ion battery needs to be charged at 126 volts. So I wanted to show you this table here to show you that, you know, the battery charger's only job is to charge the battery at the correct voltage to keep it fully charged. So when we do lose power, we have all of the capacity of the battery available to do what it needs to do. Okay, that is the charger's only job, is to keep the batteries charged correctly. And now we're going to talk about the inverter. Okay, its only job is to convert the stored DC to AC. And now it will be designed to accept the full range of voltages from the battery. Okay, now, so for an example, a lead acid battery, remember we said that was 60 cells. For an equalized charge, it needs to be charged at around about 1.38 volts per cell if we need to do an equalize. So that is around about 140 volts DC for 60 cells. Okay, and then it's also, if we do have a power failure, the battery is going to start to discharge. And then eventually it will get down to 105 volts DC, which is the industry recommended voltage for end of discharge. So the inverter will be designed to work between 105 volts to 140 volts without any issues whatsoever. Okay, and what the inverter does is it creates a synthetically generated sine wave at the exact frequency and the exact voltage required for all the specified ranges of DC. So let me see what our next wave. No, let me not do it that way. So on this one here, what we're saying is we can have 105 volts up to 140 volts going into this inverter, and the output of this system is going to be 120 volts if it's a single phase system for all of those parameters. Anywhere in between, this does not move. It stays at 120 volts if it's 105 volts, or it stays at 120 volts if it's 140 volts into the inverter. That is the inverter's job. You know, it doesn't care where the DC is coming from as long as it is between 105 and 140 for a 60 cell lead acid battery. Okay. And how do we do that? Well, I showed you that we use SCRs in the rectifier charger. In our inverters, in the majority of our inverters, we use IGBTs. And once again, don't get carried away with the fact that, oh, it's a transistor, oh, that looks really complicated. Transistors, they amplify things and they do fancy things, and oh, my brain hurts. Don't worry about that. What we use an IGBT for, just like an SCR, is just a switch. It is only a switch, and all we do is control which IGBTs we turn on to get a desired result. Okay. So the same example for the charger I'm going to do for the inverter. So remember, we have our positive over here. Now remember, that's usually going to be connected to our battery back here, okay? And if we only turn this IGBT on, yes, we will get that battery voltage and we will have positive on this side of the transformer. But because we don't have a return path to the negative, we get nothing on the output here, okay? With only one IGBT on, nothing happens. We need to have switch 2 IGBTs on so we get a return path to this negative point, okay? Because remember, electricity, we always have to get back from positive to the negative point. And also, if we just switch this IGBT on, yes, we will make this side of the transformer the same point here, because remember, we're just using it as a switch. So yes, they will be the same point, but there's no power flow because it would need to get back to this point here. So you can see where I'm going with this. Probably what we have to do is we have to switch 2 IGBTs on. So what we do is we switch this IGBT on and we switch this IGBT on. And remember, it's not we're not amplifying anything. We're not doing anything fancy. All we're doing on this transformer here is making this side of the transformer positive and this side of the transformer negative. Power flows through the transformer winding, which means a field is induced, okay? Now, if we just kept it on like that, then the transformer is going to saturate and it's going to stop working, because if anybody knows anything about transformers, they do not pass DC, but they will pass a pulse of DC like that. So let's just say we're going to do this at 60 hertz. It's not how we do things, but it's easy to get in your head what's happening with the inverter. So this pulse here is probably something, I can't remember the math, 2.5 milliseconds, something like that. Don't correct me. I can't remember the maths and the 60 hertz 1 divided by 60 and get the size of each pulse of the waveform. But all you need to know is we have created a positive pulse. And remember, we're taking this from the battery. So if we said that this was 135 volts DC, that means the size of this pulse is going to be 135 volts DC into the primary of this transformer. Okay? And then the clever thing about this inverter H bridge, and the reason we call it an H bridge, if I go back here, is because it kind of looks like an H. Okay. What we can do is, rather than switch these 2 IGBTs on, now what we're going to do is we're going to switch those off and we're going to switch these other 2 IGBTs on. Now you have to be very careful with this one and follow me through here. So remember, we still have our positive here, but now if you follow this through, we get to this point here, and now we're going through this IGBT, and it gets down to this point here. And then that goes to the transformer on this side. So we're now making the bottom of the transformer positive with respect to the top of the transformer, which is now connected to the negative through this IGBT switch here. Okay, so all we've done is flip-flopped the power on the transformer, and we now have 130 volts from 0 down that way, 135 should I say, okay, on the bottom side of the 0 crossing point. And if we add those 2 together on the primary of this transformer, if we were switching at 60 hertz like this, we would measure this waveform here on the primary of this transformer here. Okay, so from DC, we have created a rudimentary square wave going into this transformer. And with this choke here, and with this capacitor here, and with the inductance in this secondary transformer, we can convert that square wave into a sine wave. Okay, that's a very rudimentary look at how the inverter works. What we actually do, we don't switch using a square wave. We use PWM, which is pulse width modulation. And you can see this is a representation up here of what the pulse width modulation waveform looks like. And we switch at 8 kilohertz. We still create a 60 hertz output, but we're switching really, really fast. And what that does is allows us to create, you know, the mathematical average of this PWM is actually a sine wave. So it takes less capacitors and less inductance to convert this PWM waveform into this beautiful synthesized AC waveform on the output here. But that's what the inverter's job is. It is converting this positive and negative, which remember comes from the battery, which we know is going to be for lead acid 60 cells between 140 volts and 105 volts. This is going to be 120 volts, 60 hertz at all parameters between 140 and 105. This output is not going to change. It's going to be a beautiful sine wave for all of these points between 140 and 105 on the DC. Okay. So if we put it all together, all we're doing is, remember, we don't want batteries that we have to replace like AAAs and AA's. So all we're doing is we need this DC here to be charged when it's not in operation. And then when the AC input does fail, when grid power does go down, then the battery just continues to feed the inverter. And we have this beautiful AC waveform on the output as if nothing happened. It's just like pulling the plug out of your laptop. The screen stays on, all the information is saved. The battery just continues to supply power to the inverter. That is why we have a UPS. We are converting the AC into DC so we can store the charge, and then we are converting that DC back into AC on the output here, so we can use that stored charge to create something that is usable in the plant. So that's pretty much the end of the presentation as why we need UPSs, why we can't use generators, what the UPS does. You know, a lot of people are saying, well, we could, in theory, we could use to a world now where we just use DC. And absolutely we could, but the infrastructure is just not there. The infrastructure is there for AC, and it's just much easier. So, you know, I know it seems silly, but we have our UPS, so we have our AC to DC. We store our battery there, then we have our DC to AC. That goes out, and then that usually feeds for the DCS systems or for the data centers. It still goes through another power supply, which then takes that AC back into DC, usually at 24 volts DC. So we're actually converting once, twice, 3 times, where if Tesla hadn't won and we did use DC for our power distribution system, we could just use the DC to power the loads without that other conversion. But that's not the way the world works. So now I'm going to pass it out to everybody out there, see if we have any questions. Charlie says, I said 1.38 volts per cell. My apologies. For an equalizer, it's 2.38 or 2.4 volts per cell. I misspoke. I do apologize. I'm not perfect. So that's 60 times 2.4 usually, which is equal to 140 volts roughly. My apologies. Let's see what else is there. Can I return to slide 32? Why is the float voltage per cell greater than the cell voltage? I can. It's a very common question. way back. There we are here. Okay, so the cell voltage is what's called nominal. So for lead acid, the nominal voltage is 2 volts. And it's actually really confusing why they chose 2 volts, because actually if you had a battery that had been sitting off charge for a prolonged period of time, it's usually going to be around about 2.18 volts DC, roughly. Okay, it's not going to be 2 volts. I don't know why the industry chose 2 volts as a nominal for lead acid. It's just one of those things that you have to press the I believe button for and say, well, that's what they chose. That's what we have to go for. So that's the nominal voltage. The reason why the charge voltage is higher is that's the voltage that you need to maintain the charge in the cell with a minimum amount of power and losses. So the battery manufacturer works out all of its chemistry, does all of its testing. It says, okay, we have figured out that for our lead acid cell, that if you charge it at 2.25 volts per cell at 77 degrees, you're going to get the best lifespan out of it, and it's going to maintain its charge. It's a very fine line. So that is why the float voltage is actually greater than the cell voltage. And that's the same for NiCads. NiCads, they say the nominal voltage of a NiCad cell is 1.2. Sometimes I've seen it say that the nominal voltage for NiCad is 1.0. But the charge voltage for NiCad is actually more complicated, because many manufacturers say that you should charge it at maybe 1.38 volts per cell until it gets to a certain point. And then you can charge it up to 1.6 volts per cell to get the energy back into it quicker and to overcome some of the losses in that cell. NiCads are a little bit more complicated, and what the NiCad manufacturers have been doing is, because it is slightly complicated, they have now designed oversized cells so that you can charge them at 1.42 volts per cell and get all of the capacity that the data sheet specifies. It's actually, in truth, it's usually about 80% of the full capacity of the battery. But if you bought a 100 ampere hour battery, then it would actually be sized at the factory at 120 ampere hours. So when you lose your 20%, you still get your 100 ampere hours. Hopefully that made sense. So batteries are, a lot of people think that they just sit in the corner and they do nothing. They're inanimate objects, but the battery is absolutely critical. And, we do a training class here. We've got one going on just now where the guys come in and our battery trainer goes over batteries, and they come out of that class thinking, wow, I did not know there was so much to learn about batteries, because even though they are just plastic inanimate objects, they are critical to the operation of the UPS. If you have a bad battery, it's not being charged correctly, it's being abused, then your UPS is useless if your battery is not going to provide the power necessary. The next question we have is, how do we ensure that the output is perfect when the battery voltage is varying? Very good question. That's why we use PWM. I have to go through. Unfortunately, Webinar Jam is a great platform, but it doesn't allow me to select the slide. I've got to go through all of them using a next button. So how do we do it? When we get to the PWM, here we are here. Okay, so with pulse width modulation, I'm going to take a very, very magnifying glass to this portion here, and I'll draw it down here. So basically, we're creating a pulse like that. Then we are creating a pulse like that gets wider. And then we're creating a pulse like that gets even wider. And what our system can do is it can change the width of every single one of these pulses. That's why it's called pulse width modulation. So we can change every single pulse, how wide it is. And if you do the mathematical calculation of area under the curve, if we, let's for example, we reduce the size of this pulse a little bit, then the area under the curve is going to be smaller. So therefore, the output of the waveform is going to be less voltage. And vice versa, if we made that pulse bigger, then the area under the curve is going to be more, which would increase the output voltage. So we are constantly monitoring the DC going into our inverter bridge and the requirements of our load circuits using a feedback mechanism. Basically, we're looking at the output here and we're looking at the DC input here. And we are constantly adjusting every single one of those pulses to make sure we get 120 volts on the output. So for example, if the battery voltage goes down, the height of this pulse is going to go down. So the area under the curve will go down. So what we do is we will make this pulse a little bit wider now. So the area under the curve goes back up again to regulate. I hope that explains what I'm trying to say, Brent. If not, put it in the chat and see if I can explain it a little bit more. But that's how we ensure that the output is perfect 120 volts, because we are always adjusting these pulses either based on what's going on the DC or the demands on the output on the AC. And we're doing that. I know it sounds really complicated, but we're doing that 8,000 times a second. We can adjust each and every one of these pulses to accommodate whatever is going on in the outside world. And that is why our PWM systems give an absolutely beautiful, very, very consistent 120 volts AC output. Okay, let's see if there's any other questions in the chat. Okay. Doesn't seem like we have any more questions. So what I'll do is I'll do my signing off. And if anybody has any other questions, just type in while I'm saying all of this kind of stuff. I would just like to thank everybody for joining us for this webinar. We really do appreciate it because we know you guys have guys and girls, have very busy days. And to take an hour out of your day to listen to me ramble on about UPSs, I really do appreciate it. And I hope you've learned something. And don't forget, you will also receive a survey that will ask for any future topics for the next webinar. And I do read every single one of those. London will post that survey link in the chat bar as well. And I do always try and pick a topic from those surveys. So I am always giving the audience what they want to hear. The other thing that London has posted in there, she's posted a link to the where you can find the YouTube video, and there's also a link that's going to be posted if you need to contact us. It's got the 1-800 number, and it's also got the email address that you can contact the aftermarket service department on. We do have another question. Is a transformer on the output of the inverter acting like a reactor, smoothing the waveform out? Yes and no. That's a very good question. Because there is because a transformer is an inductor or a reactor, it does have inductor properties, a reactor property. So yes, it is smoothing. So on this drawing here, this is our old style drawing where we actually did used to have a separate inductor and the separate winding for the actual transformer. Now what we've done is we've designed our transformer so this inductance is built into the primary windings of the transformer itself and the secondary windings to give us the action of a reactor. So yes, basically we have an LC circuit there, and it is filtering out all the harmonics of this pulse width modulated waveform and turning it into this synthesized AC waveform. So yes, reactance or inductance inside here is a choke. Another question, do your ferroresonant inverters also use PWM? Another very good question. No, they do not. Our PWM inverters, they generate this. Okay, now they don't use an H bridge. It's a little bit of a different design. We do use IGBTs, but it's a much easier design where basically we just switch using a center tap primary transformer, and we only need one IGBT on the positive, one IGBT on the negative for small powered systems anyway, and we can basically switch the positive to that side, or we can switch the negative to that side, and that changes the direction of this waveform here. There is a video in our YouTube library that explains a little bit more about how the ferroresonant system works. And rather than having a normal transformer here, the regulation is not done by changing the width of the pulses. What it's actually done is the transformer is called a constant voltage transformer, or a ferroresonant transformer, and that transformer does the regulation. Basically, we have a tank circuit that saturates the transformer at a certain point, and the output stays at 120 volts, depending, independent of the input on this side here. So it's a slightly different, more robust design, but it's not the regulation of the output is not quite as good as the PWM circuit. Okay. Does varying AC input have any effect on the SCRs or float output voltage? Yes, basically, that is why we have to use SCRs in the charger. And it's a very good question, Rachel. And I didn't go over it. I do have another YouTube video that does go over more in depth how a charger works. But basically what happens is, if we go back to this screen here, the reason we use SCRs is because we can tell those SCRs when to turn on, okay? We can't tell them when to turn off. SCRs, you can't remove a signal from the SCR to turn it off. The only time it turns off is at the zero crossing point of the waveform, so at that point there. So we can tell, for this waveform here, we can tell it to turn on at that point there, and that part of the waveform will get through. And the reason that we do that is because we don't know what the grid power is. You know, the front of our UPS will say 480 volts, but we know that some plants are 500 volts or some plants run at 460 volts. But there's a huge variety of differences, and it changes during the day, depending on how close you are to the power generation station, how much load is on, and all that kinds of stuff. So what the SCRs do, they're always constantly monitoring the DC output here. And if we've set it at 135 volts DC, the feedback mechanism is going back to a control board. And it says, okay, if my voltage goes down here, because let's say we've gone down to 460 volts, then what it will tell the SCR to do is it will switch on earlier in the cycle and allow more of the waveform through. And once again, it goes back to the area under the curve. That increases the voltage back up again, and then the feedback will constantly work like that to maintain this 135 volts. So we are constantly changing the phase angle of these SCRs to give us the output here of a steady 135 volts. So yes, varying AC input does have an effect, but it is automatically taken care of by the feedback circuit and our control board. So a very good question, and hopefully that explains the answer. Okay, I don't see any more questions coming in. So once again, really, truly appreciate you taking the time to listen to me today. Hopefully you enjoy the rest of your Wednesday and the rest of your week, and look forward to the weekend and have a good time with your friends and family. So from me, Craig Williams, here at Solidstate Controls, we really do appreciate you taking time to watch this, and we look forward to seeing you, or well, look forward to speaking to you next month at our next webinar. Thanks very much. Take care.